Good evening. I hope my screen is visible.
Yes, sir.
Okay, I'll just wait for another minute so that maybe a few more students can join. Then I'll start the tutorial session. So this is the last week. We have almost covered, or this course is like almost finished. So this is the last tutorial. So, but there's going to be another tutorial that I'm going to take. That is like tutorial number 13. That is on next Tuesday. So I'll cover a few more questions related to some important topics like Bode plot, especially, and maybe if, PI controller design. Okay, so I'll just briefly discuss what's been covered in the last week. So we have seen the frequency response, right? Okay, so we have seen the absolute stability and relative stability. Okay, so it's very important because here in this tutorial session we are going to see the compensator design. So what does actually compensator does, right? It is compensating for something. Okay, so definitions are covered in this relative stability topic, where you cover the imported terms like gain crossover frequency, phase crossover frequency, gain margin, and phase margin. Okay, so we'll be using these compensator, lead compensator, lag compensator, or be lead lag compensator to compensate for what is missing in our plant transfer function, right? So it's very important you know the definitions of uh, this gain margin and phase margin. Particularly, we'll be using phase margin. So I'll just read out the definition. It is additional amount of phase lag that needs to be added to the phase of the system at omega equal to omega g. So this is crossover frequency. That means your magnitude becomes one to bring the system to the verge of instability, right? So this is the definition of phase margin. And what we have seen for a stable system, gain margin should be positive. Okay, like given a system whose open loop transfer function does not have pole zero in RHP, so both the gain margin and the phase margin should be positive. Okay, so this is the uh, point you should remember. Okay, okay. So definitions we have seen. What is the bandwidth, right? And in the last week we have covered the compensators. Like first is lead compensators. Okay, so why the lead compensator used? So first, what is the objective of using these compensations? Okay, so it adds sufficient phase lead to reduce the any excessive phase lag. So what is the definition for phase lag? We have studied 180 plus some phase. Okay, so if you only see PES, okay, so we don't have enough phase margin. That's why we want to compensate the margin by using a suitable compensator, right? So that's why we are using lead compensator. Okay, so it's a transfer function is given like this here. Okay, so where we have three variables kc, alpha, and t. Okay, and alpha is between 0 and 1, and t and kc are greater than 0. Okay, so correspondingly, if you see the transfer function, okay, we have pole and 0. Okay, so you can see open loop 0 at minus 1 by t, and open loop pole at minus alpha by t. So you know alpha is between 0 and 1. That's why this open loop pole will be greater than the 1 by t. Okay, or yes. Okay, so we have seen the magnitude and how to calculate the phase. Okay, and we have drawn the Nyquist plot. Okay, And from the Nyquist plot, we have a very important term, that is maximum phase. So where we are getting maximum phase, so we have to remember this formula, right? So this is derived from by seeing the Nyquist plot. Tan phi m equal to 1 minus alpha divided by 2 of root of alpha. Okay, then we can find where that maximum phase lies. Okay, and that is equal to this. Okay, and this phi m is also geometric mean of 1 by t and 1 by alpha t. So you don't have to remember the formula, you just know this is the geometric mean. So it is like 1 by t into 1 by alpha t. Okay, because you remember this, then you know what is the value of phi m. Okay, so this is the Bode plot for the lead compensator. So you can see here, so it attenuates the low frequency magnitude here. And again, what it does, you can see here, it provides additional gain at higher frequencies. Okay, so that's why we say the frequency, or it increases the bandwidth of the system. Okay, that we'll see. Okay, and a few observations are here. It is written the magnitude of open loop transfer function at low frequency is decreased, potentially leads to increase in steady state error. So we have seen, right? So more is the gain at lower frequencies, lesser is the steady state error. Okay, but in this case it's decreased because of the attenuation provided by the lead compensator. Okay, so okay. So one solution can be, you can increase the gain, but if you increase the gain, the overall gain of the compensator will also increase. So what you will do, you will end up amplifying the high frequency region also. Okay, so this is the drawback of why we don't increase the Kc, right? Okay, so we have seen at omega m the phase is maximum. Okay, that we'll be using. Okay, so this is very important example. So if you want to know how a lead compensator or any type of compensator, how it's used with a particular transfer function. So it's a plant transfer function. So you can study this example, right? So in this transfer function, it's a type 1 transfer function, okay, which was given. So we were asked to find the uh, lead compensator transfer function. So some specification is given for the open loop transfer function, right? So it should have velocity coefficient as this, and also we need phase margin to be 50 degree, at least 50 degree, and the gain margin should be this, right? So based on that, we have to find out Kc alpha and T. Okay, so this is how we proceed, right? So I'll not explain this, so you can, if you have any doubt, you can ask me. Okay, so this is very elaborative example where you can see how we can find out the three uh, parameters here of the lead compensator. Okay, so basically up to now, lead compensator is used for the to add the extra phase margin. Okay, so extra margin to the plant transfer function, that's why we are using the phase margin. Okay, so this is very important examples. Okay, so then what we have studied the lag compensation. Okay, so lag compensation is basically used for the to attenuate the high frequency component of the system response. Okay, so in the previous example for the lead compensator, we have seen from the Bode plot, it actually amplifies the high frequency components, right? So in this case, a lag, why we are using lag compensation, we are not using to decrease the phase margin as was used for the, like in the opposite sense, we are not using, we are using specifically for this. Okay, to attenuate the high frequency component. Okay, so this is the transfer function. In this case, beta t and kc are the parameters, and all those parameters are, the beta is greater than 1 and t and kc is greater than 0, and you can see open loop pole and open loop 0 here. Okay, so similar to previous case, it has two corner frequencies, right? 1 by t and 1 by beta t. Okay, so similarly you can find out here the magnitude as well as the angle. So correspondingly here it is shown the Nyquist plot of the lag compensator and the Bode plot here. So you can see here, okay. So we have to focus in this high frequency region. So you can see it is attenuating the high frequency region magnitude, right? So that's what we want, because we don't want to amplify the high frequency region, because it just uh, adds noise to the system, okay. And one important thing, it's what it's doing in the low frequency region. It is actually amplifying the low frequency region, so we can have uh, uh, increased like lower steady state error, okay. So it's shown here, okay. So lag lead compensator, so you can get the combination of all the advantage of lag and lead compensator here, okay. So you can get improve the stability margin, okay. And for lag compensator, it attenuates the high frequency, okay. This is the transfer function here, okay. So Kc, in this case, gamma, Kc, gamma, T1, T2, and beta are the variables, okay. So this is how the Bode plot of the lag leak compensator looks like, right? Okay, so you can see this is lag compensator and this is lead compensator, right? So in the middle, if you see frequencies, it is attenuating those frequencies, okay? So you have to remember this. Okay, so course summary. So any doubt you had in the theory part? So anything you wanted, or you have had any doubt while you were seeing the example problem that was discussed in the class? Okay, I'll straight away go to the tutorial questions. Okay, so very simple questions. Okay, so its first question is just the statement based. So you have to answer this, right? Which one of the following statements is true about the lead compensator? Okay, so lead compensator, it will be easy if I draw the Bode plot. Okay, okay. So this is the asymptotic Bode plot for the lead compensator. Okay, let's see the first statement. It attenuates high frequency signals and worsens the transient response. Is it true or false? Okay, so it's talking about the high frequency signals. So it's talking about these frequencies. So you can see from the body plot, so it's doing the opposite. Okay, it's not attenuating the signal, it's actually amplifying the high frequency signals, right? So, and the second statement is it worsens the transient response. No. So what it does is it increases the bandwidth, right? So also it was discussed in the lectures also. So if you have higher bandwidth, that means you have better transient response. Okay, better transient response means your system will be faster. Okay, so in this case, what we have is it amplifies the high frequency signals, and what happened in the second case, it improves the transient response, right? This is the characteristic of the lead compensator, right? So let's see where which statement is correct. So second statement, if you see, it improves the transient response, right? Because it is increasing the bandwidth. So let me just transient response. When I say, so it is like equivalent to higher bandwidth. Okay. So we have seen for the lead compensator, it increases the bandwidth, right? And it amplifies the high frequency signal. You can see, okay? So this statement is correct, okay? So it actually, this is the advantage, but this is the disadvantage, right? It amplifies the high frequency signal. That should not be there. Okay, because it will, if we see this complete system, that means you are allowing the noise, high frequency noise, to pass through the system. Okay, so any doubt in this question? Okay, so second statement is true for the lead compensator. Okay, it improves the transient response and amplifies high frequency signal. Okay, next question. A lead compensator introduces an open loop 0 at -2. Okay, this 0 is at -2 and open loop pole at -20. Okay, then the corner frequencies of the compensator sinusoidal transfer function is, so pole, what are the corner frequency for? Okay, let me write transfer function for the lead compensator. Okay, so what we have seen here, corner frequency -1 by t and minus alpha by t. Okay, and this is
Sir,
what,
plus 1
yeah,
by t.
+1 by t, where,
Sir, corner frequency 1 plus 1 by
yeah,
t.
oh, correct. So yeah, frequencies are positive. So okay, so these are positive, right? So but we also see these are what, poles and zeros, right? Okay, so okay, let's only focus on the transfer function CS. So okay, so what is the pole and zero? So its pole is minus alpha by t and 0 is -1 by t, right?
Yes.
This is correct. Okay, so we are asked about the corner frequencies. Okay, so you can relate, right? Pole and zeros. Okay, so corner frequencies are also pole and zero for this uh, uh what you call transfer function. Okay, so straightforward, it's very simple. So corner frequencies are what, 2 and 20, right? Poles are minus alpha by t and 0 is -1 by t, and corner frequencies, since they are positive. Okay, so that's why you can say these are 2 and 20. Very simple question. Okay, any doubt in this question? Okay,
No, sir.
okay. So let me, you can also, so you know now how to draw the Bode plot. You used to write like this: 2 alpha plus 1 into is alpha t plus 1. Then it's much more clear, right? So from here you will get one corner frequency, from here you will get one corner frequency, and which is equal to the poles and zeros. Okay, straightforward. And let's go to third problem. In problem 2, the maximum phase lead provided by the lead compensator. Okay, so maximum phase lead. So I told you to remember this. Okay, so we have to find out what. Okay, for this we need alpha, right? But from the previous question, what we know, 1 by alpha t and 1 by t is known to us, right? So 1 by alpha t is equal to pole is 20 and this is 2. Okay, so let me just write the transfer function. So this is known. Okay, kc alpha. Okay, this is s plus 2 and s plus 20, or let me write in this form. 1 by alpha t, 1 by alpha t is equal to 2 s plus 2 and s plus 20. Okay, so this is known. Okay, kc alpha. Okay, this is s plus 2 and s plus 20, or let me write in this form. 1 by alpha t, 1 by alpha t is equal to 2 s plus 2 and s plus 20. Okay, so this is known. Okay, Yes, S plus 2 and S plus 20. Okay, this was known to me. Okay, and I have to find out alpha. So you can put the value of this is okay. 1 by t is what 220. So alpha is what 2 by 20. This 1 by 10, right? Equal to 0.1. So also we know this is correct, right? Because alpha is between 0 and 1. Okay, so alpha is equal to zero point 0.1. So let's find out the maximum phase. So please find out this. What you're getting?
54.9
54.9.
degrees.
Okay, it's okay. 54.9. Okay, 94 you'll get 9. Okay, so this is the maximum phase that will be added by this compensator, right? I hope everyone is getting the same answer. Okay, very simple question. It's a formula based question. Okay, so in this question, what we have done, we know sine phi m is equal to 1 minus alpha divided by 1 plus alpha. Okay, so only unknown was alpha. Okay, so from the previous question, we know open loop pole and open loop 0 for this compensator was given. So here I have written 1 by alpha t is equal to 20. So this was pole, right? And this was 0. Okay, so from here I have calculated alpha. So alpha is equal to 0.1 and substituted the value of alpha in phi m. Okay, so I'm getting 59.9. Okay, 54.9. Sorry, degree. Okay, I hope everyone is getting the same. Correct answer is 54.9. Okay, so in this question, in problem 2, the frequency at which the maximum phase lead would be provided. Okay, so what I told you, this is geometric mean of 1 by t and 1 by alpha t, the two corner frequencies, right? So 1 by t is one corner frequency and other corner frequency is 1 by alpha t. Okay, so this is root of alpha into t. Okay, so let's find out. So just now we have calculated alpha, which is 0.1, and 1 by t, 1 by t is, let me write like this. Okay, so 1 by t is equal to, in the if you see the previous question, 2. Okay, so find out 2 by root of 1 by root of 0.1.
6.32.
6.32, correct. This will be radian per second. Okay, so it's a formula based question, right? Phi m, but you don't have to remember the formula, but you should know what is the transfer function for a lead compensator. Okay, so again, just get acquainted with this st plus 1 and is alpha t plus 1. Okay, because then you know what are the corner frequencies here, 1 by t and 1 by alpha t. Okay, then you know the formula for omega m, which is geometric mean of two corner frequencies. Okay, very simple question. Okay, in problem 2, it is desired that the low frequency magnitude value of the compensator sinusoidal transfer function be 0 dB, then the value of parameter Kc. Okay, so this is known to us. Okay, so low frequency magnitude it is desired that the low frequency magnitude of the compensator sinusoidal transfer function be 0 dB. Okay, so what is sinusoidal transfer function? So if you put j omega, then you will get the sinusoidal transfer function. Okay, so it is 1 plus j omega t. Okay, this is 1 plus j omega alpha t. Okay, so because we have to find the magnitude, right? So what is the magnitude for this? So I'm just doing step by step. Okay, directly you can find out. So this is 1 plus omega t square and 1 plus omega alpha t square. Okay, so this is the magnitude we have found out, and we want to find out the low frequency magnitude. Okay, so when we say low frequency region, okay, that means omega is very, very small. Okay, so if you see this magnitude, so we can neglect omega t term with respect to 1. Okay, so what we have seen when we are doing the Bode plot also. So in this case, what you'll get is only Kc into alpha. Okay, so because here we are neglecting omega t with respect to 1, and in the denominator also we are neglecting that. Okay, so that's why we are getting this, and dB if you try to find out, so you'll get 20 log basis 10 Kc into alpha. Okay, and Kc and alpha both are positive here. Okay, so we have to find out Kc into alpha, and what's given in the question? 0 dB, and this is equal to 0 dB. Low frequency magnitude is equal to 0 dB. It's already given. Okay, so this is given 0 dB. So this is given in question. Okay, should be 20 log of 10 Kc alpha. So you know when the case, what should be the value of Kc into alpha so that this becomes 0 dB? Okay, so this should be 1, right? Because log of 1 is equal to what? 0. So we know Kc into alpha is equal to 1. Okay, and previously from the previous question we know alpha is equal to zero point 0.1. Okay, this we know from previous questions. Okay, so it's very simple now, right? Kc into 0 0.1 is equal to 1. So Kc is what? 1 by 0 0.1, which is equal to 10. So Kc is equal to 10. Okay, so in this question we have to find out the value of Kc. Okay, so what was given in the question? It's given that low frequency magnitude for sinusoidal transfer function is 0 dB. Okay, and from looking at the transfer function for compensator, we know the low frequency magnitude is equal to Kc into alpha. Okay, let me highlight this. So this is the low frequency magnitude here. Okay, so in dB it is equal to 0 dB. So we know Kc into alpha is equal to 1. Okay, alpha is given 0 0.1, so you can easily find out the value of Kc, which is 1 by 0 0.1. The answer is 10. Okay, so any doubt in this question? Okay, we'll go to the next question. So from problem 6 to 11, consider a plant whose transfer function is this. Okay, so PS is, so it's a type 1 transfer function, right? Because it has one pole at origin. It is desired that the lead compensator is used to design a unity negative feedback closed loop system with this plant. Okay, so we'll be using a lead compensator as CS. Okay, so CS is of this form. Okay, so If the lead compensator needs to provide a maximum phase lead of 45 degree, then the value of alpha is around. Okay. So what is required from this lead compensator is it should provide the maximum phase of 45 degree. Okay. And we have to find out for this 45 degree, we have to find out the value of alpha. Okay. It's, so in previous questions also we have used this formula. Okay. So you have to find out alpha here. So sine 45 degree 1 minus alpha 1 plus alpha. Sine 45 is what? 1 by root 2. Okay, I think it's 0.707. So you have to solve this. Okay, I think what you're getting from here.
Sir, in the right hand side it is 1 minus alpha.
Correct, correct. So correct, correct. Thank you. So that's why I was just because I was getting alpha negative. Okay, correct. So then, uh, yeah. So you'll get here 1.707 alpha and 1 minus 0.707 alpha. So please find out the value of alpha here.
0.17.
0.17. Okay. 0.172. So everyone is getting the same answer. Please check. So it's very simple question, right? So it's nothing to do with the plant transfer function. So we have to get the maximum phase lead as 45 degree. For that phase lead, we have to find out the alpha, and we know the formula of the sine phi m equal to 1 minus alpha by 1 plus alpha. From here, we have calculated the value of alpha, right? So any doubt in this question?
No, sir.
Correct. Simple question, right? So let's find out this. If this maximum phase lead angle should be provided at a frequency of 8 radian per second, then the value of t is around. Okay. You know, again the same formula, right? 1 by root of alpha t. So it is maximum phase lead should be provided at a frequency of 8 radian. Okay, so phi m is given to us. So this is 8. Okay, then they're asking us to find out the value of t because already we have found out the value of alpha. Okay, so you're getting the question? Very simple. So this is root of point, what you got, 172 into 1 by t is equal to 8. Okay, just find out the value of this 1 by 8 into root of 0.172.
0.3.
So you're getting 0.3. I hope everyone is getting 0.3. It's a formula based question, right? Because so up to now we have just used these formulas. Okay, so you have to remember these formulas. Okay, these two formulas we have used up to now, and also the lead compensator transfer function, because then only you will know what are the corner frequencies. Okay, because if you know the corner frequency, you know the pole and zero for the lead transfer function. Very simple. So it is desired that the static velocity error constant be phi, this, and then the value of Kc is around. Okay. So what is the definition of KVE? Okay. Okay. This you have seen, right? GSHS is the open loop transfer function. Okay. So in this case, for our case, HS is equal to 1. It's already given, right? So unity negative feedback system. Okay. And also, let me just write this CS into PS, right? Into HS. So this is GS. Okay. So let's find out CS into PS. Okay. You know, CS is Kc into alpha 1 plus ST 1 plus S into alpha T, and the plant transfer function, it's already given. So it's equal to 1 by, this is the plant transfer function P of S. So 1 by S into S plus 2. Okay. So we have written CS and PS. Okay. So let's put the limit. Okay. So S into, so I'll directly write this. Okay. So apply the limits. So KV, if you apply the limit S tends to 0, the S terms becomes 0. Okay. So you'll be left with Kc into alpha into, you see, this term will be remaining because S is equal to 0 and 0 plus 2. Okay. So this is 1 by 2, right? Everything else becomes 0. Okay. So what do you have to find out? We have to find out the value of Kc. Okay. So alpha already we have found out. So alpha what was 0.172, right? Okay. So and KB is given in the question 5. Okay. So let's put these values here to find out the value of Kc. 5 Kc into alpha, it's 0.172 into 1 by 2. So it's 5 into 2, that is 10 by 172. Quickly you find out this. What you're getting?
58.13.
Correct. 48 or 58?
58.
Correct. 58.14 right. Okay. 58.1. Okay. So very simple. So static velocity error constant was given, and we have to find Kc, right? So, but to do this question, it's very important you know the definition of this, right? What is static velocity error constant, right? And since we know why we are calculating static velocity error, because the type of system is equal to 1. Okay, otherwise you'll not get you'll not get a value here. Either you'll get 0 or some infinity value, right? We have seen when we are studying this error constants. Okay, and you know again GS is what? GS is equal to CS into PS. Okay, and already everything we know, right? Just apply the limit and you will get the value of Kc. So any doubt in this question? Okay, we'll go to ninth question. This lead compensator introduces an open loop zero at around. So it's very simple. So this is lead compensation. So again, I will write the just by looking at the transfer function. Can you tell me? So what is the zero here? So I'm asking you a very like silly question because already you know.
It's 1 by t.
Okay, so zero is equal to minus one by t. Okay, so for our case, I think we have found out the value of t. So let's go to what is the value of t? T is equal to 0.3. So 1 by 0.3. What you'll get? 10 by 3 is what?
3.3.
Very simple, right? So this is open loop zero. Okay. The next question will be the lead compensator introduces an open loop pole. Okay. So just see this. What is open loop pole here? Okay. Should be minus 1 by alpha t, right? So already we have calculated the value of alpha. I think 0.172 into zero point 0.3. Hope I'm not wrong. T is zero point 0.3 and 172. So what is this value?
19.38.
And so minus 19.38. Okay. So any doubt in this? Like it's a very simple question. Okay. So you know the transfer function, you know the poles and zeros, right? And we have calculated the alpha and t values and also Kc value. Okay. That's why. Okay. Let us think next question is. Okay. So let me here write the entire transfer function for the lead. Okay. Kc. So what was the Kc we found out? Kc is 58.14. Okay, into alpha was 0.172. 1 plus st is equal to zero point 0.3, right? And this was 1 plus s into alpha. Alpha was 0.172 into t is zero point 0.3. Okay, so this is the transfer function for lead. This is lead compensator transfer function. Okay, so we'll be using this in the next question. Okay, consider the transfer function of lead compensator whose parameters have been determined in the problem 6 to 10. The low frequency magnitude of this compensator's frequency response transfer function would tend to. Okay, so as usual, yes, so there's the transfer function. Okay, and we know how to find out the sinusoidal transfer function. So I'm doing by going through steps, right? You can directly go, no problem. So this 0.3 say omega, this is 0.172, so I'm not done the multiplication. Okay, so this is the sinusoidal transfer function, and if you find the magnitude, Okay, so this is the magnitude, right? And what we are asked is the low frequency magnitude or compensator frequency response. Okay, so low frequency, or what we do, okay, we neglect the omega term as compared to 1. Okay, so is what, just this 58.14 into 0.172. Okay, and what we have to find out, okay, in dB we have to find out, can you find out what is the multiplication of this? Because we have to take at last the log of this. So what you're getting if you multiply 58.14 into 0.172,
Hence,
exactly 10, right? So this becomes 10. So 20 log of 10 is equal to, so this becomes 1, right? So it will be 20 dB. So this is low frequency magnitude. Okay. Okay. So let's plot the border plot for this. Okay, space is here. Let me, because we have calculated. Okay. So it will start from 20 dB, right? Because we just now calculated the low frequency region. So this is 20 dB. And what are the corner frequencies? Okay, so corner frequencies in the previous question is equal to, one is this, okay, 0, and the pole is at, where is the other one? Okay, 3.33 and 19.38. Okay, let me write here. Omega 1 is 3.33 and omega t is 19.38. So these are radian per second. Okay, so omega 1, it's here. Okay, let me just make space. Just skip this step. Okay, so one corner frequency is 3.33. Okay, another will be at 19.38. Okay, so I'm drawing the approximate Bode plot. Okay, so what you'll see, this is what at 3.33. So this is at, so this is open or pole. So 3.33. So what is this? Can you tell me, like, the slope will increase or decrease? Okay, so this is 0, right? This is at pole. So that's why what you have seen. So it will increase. Okay. So the slope is plus 20 dB per decade. Again, this is 0 dB per decade. So I'm not writing 0 dB. Solely I'm increasing. I'm just writing the slope for this. Okay. So this is how the Bode plot or the magnitude Bode plot for this particular compensator will look like. Okay. So any doubt in this case? So actually what this compensator is doing, it's providing a 20 dB gain at the lower frequencies, you can see here. So if you multiply this, or even because if you build, or if you draw the combined Bode plot for this CS and the given transfer function, so you'll see for that particular the combined transfer the Bode plot will, its magnitude will increase. Okay, so at low frequency region you will not find the attenuation because of plus 20 dB gain. Okay, so any doubt in this question? I hope there is, this is a very simple question. Okay, already we know this is how the Bode plot is going to look like. Okay, just now we have the information about the corner frequencies and the low frequency magnitude. That's why I have drawn this. I hope there is no doubt in this. Very simple. Okay, so which one of the following statement is true, false about a lag compensator? So here they are talking about the lag compensator. Okay, so lag compensator. So just by looking at the Bode plot, you can tell. So it's completely opposite to this, right? So what it has, okay. So here we have one corner frequency and this is the other corner frequency. And let me write this Kc into beta 1 plus St 1 plus S beta T. Okay. So just see whether this transfer function is correct or not. Okay, so you know what are the corner frequencies here?
Sir, 1 by T and 1 by beta T.
Okay, so 1 by beta T and 1 by T. So you know beta is greater than 1. Okay, so that's why you know 1 by beta T will be smaller than this 1 by T. Okay, this will be 1 by T. Or I'll write in terms of poles and zeros, right? So this is pole and this will be 0. Okay, so that's why you can see here this is what minus 20 dB per decade decrease, because at omega 1 you have encountered a pole, that's why the slope will decrease. Okay, and again at omega 2 you will encounter a 0, so that's why again the magnitude increases, not increases, it stays constant. The slope is equal to 0 dB per decade. Okay, so this we know. Okay, so let's answer this. So you have to find out which statement is false. So first is it attenuates high frequency component. Okay, so just look at the high frequency component greater than omega 2. So it is attenuating or amplifying. Tell me whether this is first statement is true or false.
Attenuating.
Correct. So this statement is true, right? Okay. So we are talking about this region, right? So this is attenuation, right? So if to give it like some values, let's assume this value is minus 40 dB, right? So if you, what it does, okay, so you'll have some plant transfer function. At higher frequencies, you are going to add this minus 40 dB to that magnitude. Okay, so it will, what it is doing, it is actually decreasing the magnitude at higher frequency. So we are decreasing the magnitude, that means we are saying we are attenuating high frequency component, right? So first statement is true. Second, it increases the low frequency gain. So it talks about this, true or false. Okay, so let me write this, it can be like 20 let's assume this is 20 dB. So what it does, is it increasing or decreasing the gain at lower frequencies? Because you are going to add this gain, right?
Sir,
In the,
constant.
yeah, so it increases the low frequency gain means I'm saying you'll have a plant, right? So plant transfer function you have, and it will have some Bode plot. Okay. So what we are doing is we are adding the magnitudes in dBs for this particular compensator and that given plant transfer function. Okay. So at lower frequencies, it is actually adding plus 20 dB to that whatever the gain of that particular transfer function is. Okay. So we are actually adding 20 dB. Let's suppose. So plant transfer function is not given. So okay, let's suppose we have this some plant transfer function PS we have. Okay. So it has some let's assume it has 0 dB, right? At low frequency, it has 0 dB. Okay. So what you will do, because you know GS is PS into, sorry, CS into PS, right? And this is in dB. So let me write P of J omega. Okay. So this is in dB. Okay. So in dB, what you do, 20 log of Cj omega plus 20 log of Pj omega. Okay, so you are going to add that. Okay, so assume in this frequency region, low frequency region, okay, you are adding 0 dB plus 20 dB, right? So effectively your gain has increased, right, at low frequency. So we'll be adding these two. Okay, so this is CS and this is PS. And GS is what? CS into PS, and dB, you know, it is the addition, right? That's why we are taking in dB. One of the advantages we have studied, right? Multiplication is converted to just the addition in log. Okay, so that's why 0 dB, just for example, is now being added with 20 dB gain. So effective gain is increased to 20 dB. Okay, so that's why second statement is true, which is saying it increases the low frequency gain. Okay, so any doubt in this case?
No,
That's
sir.
what for the first statement also this holds true, right? I'm minus 40 and I have some gain here. Okay, so this is the gain. Let's suppose this is the high frequency gain and I'm decreasing further because what I'm doing, I'm adding minus 40 dB. So whatever this gain was there at high frequency, I'm reducing further. So that's why I'm attenuating, and in the low frequency, I am increasing. Okay, so this statement is also true. And let's see the third statement. It reduces the steady state error. Okay, so your gain at low frequency depends on steady state. Like steady state error depends on what is the gain at low frequency. Okay, that we have seen. Okay, so higher the gain at low frequency, okay, the less will be the steady state error. Okay, so this is also true. Let me write here. Okay, higher the gain at low frequency, lesser the steady state error. Okay, higher. So we have seen in the second statement, you know, the gain at low frequency is there, higher gain is there. So that's why now we'll have lower steady state error. So this is also true. Last statement is increases the system bandwidth. Okay. So all the statements are true. So only this will be false. But what is the implication of this? How it reduces the bandwidth? Okay. Just the key, we are multiplying these two transfer functions in Bode plot. Okay. So what will happen is this frequency. Let me choose this frequency. Okay. So what we are actually doing is at higher frequency, this frequency will be reduced here. So it will come here. Okay. So combined plot will, so if you combine the plot, so that will have this omega c nu. Okay. Because of this attenuation at higher frequencies. Okay. Because of this, you'll have new gain crossover frequency. Then we will say the bandwidth of the system is reduced. Okay. So any doubt in this? Okay, because you're going to multiply these two transfer functions. Okay. And effective Bode plot you're going to draw. So at higher frequencies, what is happening? It is attenuating the higher frequencies component. Okay. So your omega c will effectively reduces in this case. Okay. So that's why you will get lower bandwidth. Okay. So lower bandwidth means sluggish response, because bandwidth is related to the transient response. Okay. More is the bandwidth, better is the transient response. But on the flip side, what is happening? You'll get higher frequency noise. Okay. So this just say this will become this. Okay. Which is in compensated network. Okay. That's why the bandwidth reduces. But in this case, it's written wrong. It increases the bandwidth. Okay. For lead compensator, that is the case. Okay. So any doubt in this question? Okay. Also on the theory also we are seeing, right? Okay. 13th question will go. A lag compensator introduces an open loop pole. Okay. This is open loop pole 0, sorry. And open loop pole. Okay. Then the corner frequencies of the compensator sinusoidal transfer function is, okay. So from the Bode plot also, right? What is pole? Omega 1 was pole, right? And omega 2 was 0. So what is omega 1 here? Just the positive. Okay. Can you tell me? Just see this Bode plot. First we
Sir,
encounter the pole.
5 and
Correct.
20.
Correct. First we encounter the pole. Pole is at 5. Okay. And the 0 is at 20. Simple. 5 and 20, right? Very simple. You know the transfer function, right? And also you know the Bode plot. Omega 1 is equal to pole, omega 2 is equal to 0. Okay, that's what it is asked. Pole and 0 is given and they're asking the corner frequencies. Okay. So 14, consider a lag lead compensator where omega 2, sorry, T2 is greater than T1. Then which one of the following statement is true about the two open loop zeros and two open loop poles? Okay, so let me just draw the Bode plot. You tell me which one is correct. Okay, so I'm drawing the Bode plot for the lag lead compensator. So one is this. Okay, so which one is correct?
So first one.
Okay, so first one is correct, right? Okay, so this part, at least. What is this part? So you've seen the Bode plot for
Sir,
individual lead
lag,
lag, right?
lag compensator.
Okay, so this is lag compensator, correct. and the other part, this is equal to lead compensator. Okay. Let me just erase the other one. Okay. So the transfer function for this is Kc, okay, 1 plus T1 S plus gamma T1, okay, S plus 1 by T2 plus beta T2, I think. Please see if I'm making any mistake here. Okay. We try to mark the corner frequencies here. You tell me what are these corner frequencies. Okay. So omega 1, omega 2, omega 3 and omega 4. So what we have studied, okay, so this was the lead compensator. Okay, so the other part was lag compensator. Okay, so T1 and gamma are related to lead and T2 and beta are related to lag. Okay, so first, you have correctly pointed out that the first portion is lag compensator, right? So lag compensator, that means T2 and beta. So what is omega 1? At omega 1 we have a pole. That's why the slope is decreasing. So what is pole here?
So 1 by beta T2.
Correct. Right? 1 by beta 2. So I will also write pole. Okay, so only one omega 2 is again 1 by T2, right? So this is 0. And we go to omega 3. Okay, so we'll encounter what? Because now the magnitude is rising after omega 3. So that means we have a pole. Okay, so that pole is 1 by T1. Okay, and this is 0, and this will be, sorry, alpha by T1. So this will be 0. Okay, just see this. Okay, so let me just increase the gap between this transfer function and, okay. Okay, first you have written down the transfer function and now you know the corner frequencies also. Okay, so let's try to answer this question. Okay, so first statement is the two open loop poles would lie between the two open loop zeros. Okay, somewhere I have written wrongly. So this was a pole. Okay, so first statement is two open loop poles would lie between the two open loop zeros. Is it correct or what? You tell me. What are,
Sir,
what are two? Correct. So these are open loop poles. Okay, and what the two open loop poles would lie between two open loop zeros. That is like completely opposite, right? Because two open loop zeros are lying between two open loop poles. Okay, so these are zeros. Okay, these are okay zeros and these are poles. Okay, second, this is false. The second statement, two open loop poles would lie between the two open loop zeros. Okay, I think first statement I So it is like not lie. Okay, let's answer the second statement first. The two open loop poles would lie between two open loop zeros. Okay, so this is false. Okay, and the first statement was the two open loop poles would not lie between the two open loop zeros. That is correct, right?
Yes, sir.
Two open loop poles would not lie between the two open loop zeros. That is correct. So let's go to the third statement. The open loop poles corresponding to lead compensator. So you know where is lead compensator and what is the open loop pole? The last corner, omega 4 you see. Okay, why written wrong? Okay, 4. You see omega 4. Okay, that is the open loop pole corresponding to lead compensator would lie between two open loop zeros. No, right? So this statement is also false. Clearly, you can see the two open loop poles, the open loop pole corresponding to lead component would lie between two open loop zeros. So nothing is lying between two open loop zeros, right? Okay, so let's see the last statement. The open loop pole corresponding to lag component. Okay, so what is the open loop pole? That is omega 1. Okay, would lie between the two open loop zeros. This is also false because both the poles are lying at the extremes, right? Omega 1 and omega 4 are the poles. Okay, so clearly third and fourth are wrong. And the second statement says the poles are lying in between the zeros, which is completely false. It is actually the opposite, which is said by the statement first. You just see, okay, where the open loop poles and zeros are lying and which one is matching. If you have a doubt. I hope there is no doubt in this question. It's just straightforward, right? Look about the location of poles and zeros of lead and lag compensator. Okay, let's go to this question. Consider the magnitude plot of the Bode diagram of the typical lag lead compensator. One can conclude that. Okay, let me just copy this same plot. So you do answer by looking at this plot. Okay, one can conclude that the high frequency components are attenuated. So what do you say about this first statement? Let's go statement by statement, right? So let's try to like comment on this first statement. The high frequency components are attenuated for this Bode plot. What can you say? So only two options are there, right? You can attenuate them or amplify them. So what this compensator is doing at high frequency,
Sir, amplified. So it
correct?
is.
So correct. So at high frequency, you can see the magnitude is high. So since I've drawn the low frequency and high frequency magnitude to be same, but they will not be same, right? So I've drawn like these two same high frequency and low frequency, but they're not same. But this statement is false because we can see at high frequency the magnitude is high. Okay? Let me say like 40 dB. Okay, let's just to give you a quantifiable magnitude 40 dB. Okay, so if you multiply this CS with the plant transfer function, so in dB what you're doing, you are actually adding some gain, right? At higher frequency, whatever the gain you will have for the plant transfer function, let's suppose it has a gain of 6 dB or 10 dB at higher frequency. So what you are going to do, you are going to add 10 plus 40. Okay, so what you're doing, you're amplifying the high frequency component because now what is the final gain at high frequency 50 dB, right? So that's why we are saying it's amplifying the gain. Okay, so the first statement is wrong. So let's check the second statement. The low frequency components are attenuated. Again, the same case. Okay, here the low frequency component is not attenuated. Okay, you can see the same logic also is valid for the low frequency region also. Okay, third statement is intermediate frequency band is attenuated. So you can see intermediate frequency band is this band. So you can see the magnitude is lower, right? So let me just say this is equal to some minus 10 dB. Okay. So if you add CS and PS, what you will do in this omega 2 to omega 3, you know, the gain will be reduced by a fact by minus 10 dB. Okay, so that's why it's attenuating, right? So this statement is true. You can see from the Bode plot also. Okay, omega 2 to omega 3, you're attenuating the gain. And the last statement obviously is false. The intermediate frequency band is amplified. It's not amplified, it's attenuated. Okay, we'll choose the gain such that this statements hold true, whatever I have discussed now. Okay, so at low and high frequency, we are amplifying the signals or amplifying the high frequency and the low frequency component, and between the intermediate band will be attenuating. Okay, so any doubt in this case? Okay, we have reached to the end of this. Okay, so any doubt for any question that I've discussed today? Okay, let me go through all the questions. So 15 was about lag lead compensator. Okay, so you know it is just about the basic definition of lag lead compensator. Okay, first why we have this lag lead compensator. Okay, we discussed that, and 14th statement is also related to the same. Okay, about where the corner frequencies are. Okay, so where the lag compensator poles and zeros lie and where the lead compensator lie. Okay, so looking at the transfer function, you can plot the corner frequencies and then you can know where the poles and zeros are lying. Okay, so we have seen that. And 13 was related to lag compensator about the pole and zeros. Okay, and this was about the lag compensator. First of all, why we are why we require the lag compensator, right? To attenuate the high frequency components. Okay, so one of the drawback for the lead compensator was, okay, it amplifies the high frequency components. So though your bandwidth has increased, but you are allowing the noise. So there will be issues like EMI, EMC, high frequency noise that will come into your system. Okay, so that will pollute the system. So what you want to do, you want to attenuate the high frequency component. For that, you require the lag compensator. Okay, so you see at higher frequencies, so I've given the example here. So at higher frequencies, it is attenuating by a factor of minus 40 dB. Okay, that's why we need lag compensator. And the 11th question was about lead compensator, about the design of the lead compensator. Okay, so 6 to 11 was about the design. We have to find, so in order to design the lead compensator, you require three parameters, right? Kc, alpha, and T. That's what we have done. Okay, for the given requirement, we have found out the values of these parameters. Okay, and the previous question was also about the lead compensator. Okay, so this was just 1 to 5 was only about the lead compensator. Okay, very simple questions. Okay, corner frequencies to find out the maximum frequency at which at which you will find the maximum phase. What is the maximum phase? Okay, very simple questions we have done here. So any doubt for today's session? Okay, so I'll be taking one extra session that is on next Tuesday. So may I know when you have your NPTEL exam for this course?
Yes, sir.
So when you have the exam, do you know? Can you tell me the dates for the exam for this course?
That's we have to check.
Okay, so okay, so I hope like for the next Tuesday because it is not before the next Tuesday. So I'll be taking one more session. So in this session, I'll be including few more questions, maybe some good gate questions or ES question or some competitive exam questions. Okay, based on the design of the systems. Okay, so we are done with the course. Okay, so this is just a classical control theory. Okay, so model control theory. So we have studied the state space representation, right? So that is the modern control theory that we use for the nonlinear system because mostly our systems are non-linear, and in order to like in order to have a better control, we utilize the state space. But the crux of the control theory is this classical control, right? Because we have to know all these definitions in order to build the controllers. Okay, so we are just seeing the basic type of controllers, PI controllers, because even now like 90% of controllers are PI controllers basically. Okay, and again these compensators are also, you can say, these are PI controllers. Okay, so any doubt you want to ask me? Okay, then uh, I have one more session, so that is on next Tuesday. Okay, so that is 2 hour session, so that is extra session, so I'll be taking a few extra questions there. Okay, so before, if you are writing NPTEL exams, so it would be a good practice if you attend that session, because I'll discuss few more questions, okay, which was not part of this tutorial sessions. Okay, so it will be on next Tuesday, same time, 6 to 8.
Okay, thank you, sir.
Okay, so
Thank you.
thank you. If you have no doubt, then I'll end the session for today. Okay, so thank you for attending the session. So I'll meet you in the next session, that is on Tuesday next week. Thank you.
Thank you.
Thank you, sir.
Thank you.